So as I mentioned before, this first day is going to be review of stuff that you have already been taught. So since it's review, my hope is that it's going to come right back and you'll be like, oh my gosh, I totally remember that now. So we're going through first our rules of exponents. And we have different rules for our different operations. So if we are multiplying two things that have the same base, that's the key thing here, is they need to have the same base. Then you're just going to add your exponents. So in my example over there, I have x to the a times x to the b equals x to the a plus b. I always like to give a number example. X to the third times x to the fourth. When we're multiplying those, we add our exponents, so it becomes x to the seventh. 3 plus 4 gives us 7. So multiplication, you add your exponents. Division, again, key thing here is it has the same base, which our base in our example there is an x still. When you divide, you subtract your exponent. So again, if we get a number example, so I have x to the 6th divided by x to the 5th, what would we get? X to the 1st. So division, we subtract. And it's always the first one minus the second one. So 6 minus 5 gives us our 1. Yep, you don't have to put that first power there at all. Nope, you can just leave it as x. That's correct. Power to a power, or exponent to an exponent. Sometimes once it's said that way, a lot of people realize what we're talking about. So that means you have two exponents there, and there's always a parenthesis. So here we have an exponent inside the parenthesis that's raised to another exponent. When it's done like that, that's when we multiply them. So a lot of people have a tendency to get these confused. By multiplying the x's, I add my exponents. If I have just two exponents and only one x there, I multiply those exponents. So my example would be x to the 3rd to the 4th power would turn into x to the 12th. Okay, power of a product. That just means if you have an exponent outside of a set of parentheses, you need to give that exponent to everything inside the parentheses. So that's why it becomes x to the a, y to the a. So for another example, if I have x, y to the 4th, it turns in x to the 4th, and then y to the 4th. Power of a quotient, same exact thing. Whatever's in those parentheses, you're going to give that exponent to everything in there. So the p goes to the x and to the y in the denominator. And same thing would happen in your numbers. It would go to what's in the numerator, and it would go to whatever is in the denominator also. Zero exponent, everything turns to a 1. Anything to the 0 power turns to a 1. Now the one that a lot of people have a tendency to mess up on is an example like 4x to the 0 power. Now because there aren't any parentheses, what is that exponent on? It's only on the x. It's not on the 4. So for this one, the 4 would stay as a 4, and only the x turns into a 1. So then 4 times 1 gives us a 4. If there were parentheses around it, that's when the whole thing equals 1. So that's the tricky part you have to pay attention to. Parentheses really do change the whole problem. And then negative exponents, we can't have negative exponents. If they're there, you need to fix it and make it positive. So if we remember, everything, if it's not already a fraction, is always over a 1. It actually is a fraction. We just get kind of lazy. We don't always write that over 1. So if you have a negative exponent, you just have to move it to the other part of the fraction, and then that moving of it turns it into a positive exponent. So that's why x to the negative p, once I move it down here to the denominator, it now becomes positive, 1 over x to the positive p. So I find examples are always the best. So let's do some examples first. So if we take a look at example 1, we have a couple of different rules in combination here. First, we have an exponent on the outside of the parentheses, so I want to make sure I give that to everything inside the parentheses. So it's going to go to the x and it's going to go to the y. But in doing so, I now have an exponent. This exponent is raised to another exponent, so that's when we multiply them. So this becomes x to the positive 8, because my negative 4 times my negative 2 gives me a positive 8. And then for the y, again, we're going to multiply because we have an exponent to an exponent. So 2 times negative 2 gives us a negative 4. And so then if we look at that answer, we have a negative exponent, which we cannot have. Negatives are bad. So I'm going to put this over 1 because it's not already a fraction, but it actually is. We just don't have it written as a fraction yet. And only the thing with the negative exponent is going to move. So I'm just going to move my y to the negative 4 down to the denominator. So our final answer would be x to the 8th over y to the 4th. Bless you. Okay, example number 2, we have some bases of 3 and we have some bases of 4. It's just like if they were x's and y's. So we are dividing here, so we need to do our division rule. What do we do with our exponents when we're dividing? Perfect, subtract them. So 3 minus 6 gives us 3 to the 3rd. And then 3 minus 2 gives us 4 to the what? 4 to the 1st, but we don't have to write that one. Now, since these are numbers, we can't actually leave our answer like that. We have to simplify it down to one number. So you can use your calculator to help you if you need to. 3 to the 3rd power is going to be what? 27. So really we have 27 times our 4 to the 1st, which is just 4. So what do we get when we multiply those? 108. So there's our final answer, 108. Example number 3, that's kind of like what I was talking about in the 0 exponent. That 0 exponent is only on one thing in there. What is it on? The z. So only your z turns into the number 1. The 5 and the x stay exactly like they are because they don't have it. So then 5x times 1 just means our final answer is 5x. Okay, example number 4, do we have any like bases? No. I got a base of 3, I got an x, I got a 4, and I got a y. So I can't use any of our rules up above because we don't have any like bases. So what I have to do though is I see a negative exponent here, so I need to move that one down to the bottom. And then my y has a negative exponent, so I'm going to have to move that one up to the top. It goes both ways. So in our numerator, the x is still there, but I'm going to add to it the y, and it's now to the positive 3rd because I moved it. And then in our denominator, we have the 3 squared, and then the 4 is still there because that one didn't move. So all we have to do now is clean up the denominator because we can't leave it as 3 squared times 4. So again, our numerator is going to stay the way it is. So yeah, some of you can probably do this in your head. Probably most of you can. 3 squared is what? 9. And then 9 times the 4? 36. All right, example 5, we have a like base. We have a base of x. We're multiplying them. So what do we do with our exponents? Add them. Perfect. So we have 2a plus 1a would give us x to the 3a. And then example number 6. Anybody have any ideas on what we should do first? Well, okay, let's take a look. I don't have any common bases in the top and bottom, so we won't add. We're going to do some division rules. What do we do with division? Subtract them. So for now, I'm going to leave the 6 in the top. I'm going to leave the 9 in the bottom. So when I subtract, I have a k with an exponent of 8, and in the denominator I have k with an exponent of 1. So 8 minus 1 gives us k to the 7th. So then I'll do my n's next. So we have 4 minus 7, which would give us n to the negative 3. And then for our p's, we have 7 minus 4. So that would give us p to the 3rd. So now we have one thing to move. What do we have to move? The n, perfect. So n to the negative 3rd, that's going to get moved down there with the 9. Now can we reduce the 6 and the 9 though? Try to do two things in one step. Is there a number that goes into both 6 and 9? 3. So 6 divided by 3 gives us 2. And then we still have k7 p to the 3rd in the numerator. And then 9 divided by 3 gives us 3. And then we have n to the positive 3 with it. So some of those, they take a little time because you have to refresh yourself of the rules. So don't just rush through them when you're doing them in your homework tonight. All right, so let's take a look at the back side. So we have a polynomial in a single variable x is an expression which can be written in the form, and I know that looks very overwhelming. So you got a sub n and then x to the n. N just refers to which term you're in. So if it's in the first term, your n is a 1. N minus 1 means it keeps going down, so on and so forth. So it tells you right here, n is a non-negative integer. Your coefficients in there are the a sub n minus 1, so on and so forth until you get down to 2, 1, 0. N is your degree. Do you guys remember what a degree of a polynomial is? It's just whatever the largest exponent is. It tells you how high the degree is. The degree actually tells you a lot of information. If you have a second degree equation that tells you you're going to have 2 answers, you would have 2 roots when you graphed it, a whole bunch of stuff. So n, so that first one, that is whatever your degree is. And then a sub 1 x to the first is called a term. So this is 1 term, 2 terms, 3 terms, so on and so forth. So this chart should look very familiar. This chart is from Math 9. They literally copied and pasted it. So example number 5, do we have any variables here? No. So this is a degree of 0 because there's no variables. So if you have a degree of 0, that's called a constant. There really is no leading coefficient here. And then constant is 5. So our next example, our 3x plus 2, what's the exponent here on the x? So 1, so this is a first degree. So if it's a first degree, we call that a linear. As I mentioned last time, we're not really going to do too much with linear. You guys did a lot with linear so far. Our leading coefficient. So you just look at your first term, whatever that coefficient is, that's your leading coefficient. So our leading coefficient here is a 3. Our constant term is the 2. Whatever number's there without a variable, that's your constant. So our next one, what's our degree? 2. Anybody remember what a second degree is called? I heard somebody say it perfect, quadratic. We've done quite a bit with quadratics already. We're going to do quite a bit more with them. What is our leading coefficient? 2. And what would our constant be? 1. All right, our next one is what degree? 3. Anybody remember what a third degree is called? Cubic. They're cubic. Just wait until we graph it. That one's so much fun. All right, our leading coefficient is 1, and our constant is -1 this time because it's -1. All the other ones were positive. Sign goes with it. Okay, next one is a degree 4. Do you guys remember what a 4th degree is called? Quartic. Good job. Our leading coefficient is a 5. And our constant term is -6. Now, is our next one in standard form? No. So we got to put it in standard form first. Which term should come first? Oh, perfect. -17 x to the 5th should come first. Which one should go next? -2x to the 3rd. And then our 6x. And then lastly, our 20. So this is a degree 5. That's our largest exponent. This one is called a quintic. That's a new one. We didn't do quintic when we were in Math 9. So our leading coefficient, -17. Our constant is 20. So we went through this because you should still remember by degree what they're called. So if I talk about a linear, that word should be sinking in there. Okay, she's talking about an example like this. If I'm talking about a quadratic, you know it's got an x squared term in there. Cubic, it's got the x to the 3rd term. So you've got to make sure you know what those words mean. Okay, so consider this expression right here. 2x squared plus 3x minus 7. How many terms does it have? I heard somebody say it. It has 3. What separates our terms? The signs, your plus sign and your minus sign. So we have, this is our first term, there's our second term, there's our third term. They want us to evaluate this expression without using your calculator, so we're going to try to use our brain powers here, when x equals -3. So that means we go through, and wherever we see an x, we are going to plug in a -3. So remember our rules of exponents, or I'm sorry, our rules of order of operations. Exponents comes first, so -3 squared becomes a +9. A lot of people tell me -9. That's +9. And then 3 times -3 is -9, -7. 2 times 9 gives us 18, -9, -7. So our final answer, 2. All right, then part C, what is the sum of the expression with this other one, 5x squared minus 12x plus 2? First thing, sum tells us we're doing what with the 2? Adding, good. So we're just going to want to line up our like terms. So I'm going to put my 2x squared under here, put my little plus sign in front of it since I'm adding them. Line up my 3x under the other one, and then my -7 under the 2. If it's too small, you can rewrite it. So 5x squared plus 2x squared. If you remember, when you're adding these together, you only add the numbers in front. Your exponents stay the same. When you're multiplying that, your exponents change. -12 plus 3 would give us a -9x. And then 2 minus 7 would give us a -5. 7x squared minus 9x minus 5. questions so far? No? All right. I'm going too fast. Just say something. I will slow down. Okay. So now we have the procedure for simplifying a linear expression is shown below. State the number properties that justifies each step. So we have to remember our number properties. Those are your commutative, associative, distributive, identity, all those wonderful properties. So they went from the left side over here to the right side of the equal sign. What did they do? They distributed. So we used our distributive property. So again, from here to there, what did they actually do? Well, really, they kind of did two steps. They went from up here down to there, and then over to the right. This one's tricky. Didn't they group some stuff together here? What's that property that allows us to group things? Associative. So we used associative property. And then to get from there to there, they just simplified. They actually multiplied your 8 times 2 and then your 5 times 3. So now from this step down to here, what did they do? Doesn't look like much of a change. It's a very subtle change. They changed the order. It was 16x plus 24, but now they put the 15x there. So they switched the 15x and the 24. Which one allows us to change order? Commutative. And then our last step, even if you can't think of a property, what did they actually do? They actually added their x's and their numbers, right? So we just call that combined like terms. So that's not really a property, but that's what they did. They combined like terms. So we have some examples here. They want us to simplify the expression, so that means get it down to as few terms as you possibly can get it. So what would we want to do first in number 1? Distribute. We have 2 distributings to do. You have to go through the first parenthesis, you have to distribute your 2, and then through the second one you have to distribute your -7. So 2 times my 1/3 would give me a 2/3 x squared. Two times my -5/3 would give us a -10/3 x. And then the easy one, 2 times 6, gives us a 12. So then we'll distribute the -7. So this is really like a 1/3 x squared. That's just another way of writing it. It's just x squared over 3. That's the same as 1/3 x squared. So -7 times 1/3 is -7/3 x squared. And then the -7 times 2/3 is -14 over 3x. So -14/3. And then -7 times -4 gives us a +28. So last step, we got to combine our like terms. 2/3 x squared minus 7/3 x squared. Who knows it? 2/3 minus 7/3. I heard somebody say it. Negative 5/3 x squared. Awesome. So then our x's, we have negative 10/3 minus 14/3. What's negative 10? No. Negative 8. The way we got negative 8 is the negative 10 minus 14 would have given us negative 24/3, which that simplifies to give you an 8. And then our 12 plus 28, that's the easy one. Plus 36. So here's our final answer. Now, if you can't add and subtract fractions in your head, what can you always use? Calculator. Calculator is always there to help you. It is. See? We all make mistakes. I'm glad you guys actually caught it, though. Some of my other classes would have just let me go with it and never said anything. Better to say something. Okay, number 2. Do we have anything to distribute? Yes, the negative. You got to make sure all these terms in the second set of parentheses, you got to change their signs. So the first set of parentheses, those aren't going to change. That's still 2x squared minus x cubed minus 9x plus 1. Yes, you can. So all I did is I changed the signs of the second one and I lined up my like terms. So negative x cubed, I put under my other x cubed. Negative 7x, I put under my other x. 3x squared became positive 3x squared. 1 became negative 1. So if we combine our like terms, 2x squared plus 3x squared gives me 5x squared. Negative x cubed minus x cubed would be negative 2x cubed. What do we get for our x's? Negative 16x. Our 1's would cancel each other out because you have 1 minus 1 would just give you 0. But I cannot leave that as my final answer, and I know some of you already changed it to put it in the correct form. Our standard form means my x cubed has to go first. So there would be our final answer. So 3, we're multiplying a binomial times a trinomial. So all we have to do is use our distributive property twice. So we're going to distribute first the x through the parentheses with the trinomial. So x times x squared. That goes back to our rules of exponents. You would add those, so we get x cubed. X times negative 5x. Would give us negative 5x squared. And then x times the 2 would give us a 2x. So now we distribute the negative 3. So negative 3 times the x squared gives us negative 3x squared. Again, I like to line up my terms. You can just keep writing right afterwards if that's the way you prefer. Negative 3 times negative 5 gives me a positive 15x. And then negative 3 times 2 gives us a minus 6. So then combining our like terms, I get x cubed minus 8x squared plus 17x minus 6. What do you think we should do for number 4? remember, if we're doing order of operations, we have a multiply, a subtract, and a multiply. So which one comes first, Brandon? I would do that after you've multiplied the two of them together. Okay? Just because then it makes it a little harder. So what you want to do is you want to multiply these ones first. So our x times x gives us x squared. Then your x times your negative 3, that gives us a negative 3x. And then distribute your 3, so now we have a positive 3x, because 3 times x is 3x. And then 3 times negative 3 gives us a negative 9. So what happens with my negative 3x and my 3x? Cancel. I heard you guys say it. So that just turns into x squared minus 9. So then over here, we'll do the same thing. Give you guys a minute. Let's have you do that one. After you multiply, you should get x squared minus 16. Now notice, I kept mine in the parentheses because we have to remember to subtract all of this, not just the first term, which is what usually happens if you drop your parentheses. You got to subtract that whole thing after you multiply. So now it's like what we did up above. Distribute your negatives, so we really have x squared minus 9 minus x squared plus 16. What happens with our x squares? Cancels. So then negative 9 plus 16. Anyone? Negative 9 plus 16? No, that's what I would say. It's not actually 5. 7. I made that mistake yesterday. So what do you think is going to happen in number 5? Pretty much the same thing, only they used different letters and they didn't put any numbers in there. So let's have you go ahead and try number 5. So remember, multiply out the first two, multiply out the second two, and then do. So after you multiplied, you should have gotten a squared minus b squared after you combined your like terms for the first one, and then a squared minus c squared for the second one after you combined your like terms. So I saw some of you already went ahead and you distributed your negative sign there. And then when you did that, you saw that your a's canceled out. A squared, so we have negative b squared plus c squared. That is our final answer. Last one on this page. We have x plus 3 squared minus x plus 4 squared. Whenever you have something squared like this, you want to write it out twice. So it's x plus 3 times x plus 3. And then it's minus x plus 4 times x plus 4. Now, before you go through and multiply all those out, I'm going to show you a little shortcut. I'm going to use x and y for now. There's a little shortcut if you have something squared like this. What it is, whatever's first term in your parentheses, that's going to be squared. That's your first term when you square the whole thing out. Plus 2 times x times y. So whatever the two terms are, multiply them together and then multiply them times 2. And then plus whatever the second term is squared. So that's a little shortcut instead of writing them out twice like I did. So you could just skip this step and then follow the rule. So x plus 3 squared would start with x squared. You take your first term and you square it. Then it's 2 times x times y. So it's 2 times x, that's 2x, times 3. So that would be 6x is our middle term. And then it's the last one squared. So 3 squared would be 9. And then it would would be minus, and we'll do the same thing. Okay, so it starts with the first term squared, so x squared plus 2 times x times 4. That would give us an 8x. And then plus the last term squared. That would give us 16. So that's just a way to help you go a little faster, because there's going to be some problems where you got little things like that squared. If you can memorize that shortcut, it's going to make your life a lot easier. So then the last thing we have to do is distribute your negative and then combine your like terms. Hopefully when you combine them, you get negative 2x minus 7. Your x squares cancel. And we get negative 2x minus 7. All right, I think we got one more page. Yeah, we do. Okay, so we're just filling in some blanks. So we have a binomial times a trinomial. So first I can tell they distributed the a through. So what would be our second step? Distribute the b. So this should be a bc, and then bd, and then be. Now the second one, this is using the little shortcut. They took the first term and they squared it. And then they did 2 times the first term times the second term. And then, so what should this last one be? Should be your second term squared. That's our little shortcut we were just doing. Number 3 is getting a little bit into factoring. This was our dots factoring. What number should we have on the line? Very good. Okay, so if I multiply these, what do I do with my exponents again? Add them. So this would be 2 to the 42nd power minus 1. And then you would finish from there and actually figure out what the one answer would be. So number 5 here, what it's trying to get you to do is trying to think about what would your last term or your first term be without actually multiplying the whole thing out, because you don't always need to actually multiply it all out. So if we look at A, we would first start distributing at the beginning, wouldn't we? So we would distribute this and we would get a 2x squared, and then, go to my x, or my 5x there. And then with the 4, I would get a plus 8. And I only did those two because, again, we're looking for just our first and our last term. I don't really care what the middle term is. I'm just trying to look at the first and the last one. If I distributed over here, I would get x squared as my first term, multiplying my two x's. Our last term would be the two numbers multiplied together, so that would be a plus 6. Again, I don't really care what the middle is because they're just asking us for the first and the last. So if I combine my x squares, what would our first term actually be? Yeah, it would be 1x squared. Because you would have this 2x squared, and since it's subtraction, you would subtract that 1 from it, so we would get 1x squared. And then what would our last term be? What would our 8 minus 6 be? 2. No, it's minus, so it's 2. For B, I could sit here and write that out 10 times and multiply, but we don't need to do that. Our first term will always be whatever this is to that exponent. So our first term would be x to the 10th there. Our last term would always be the last term in the parentheses to that exponent. Which again, we could sit here and do that in the calculator, but that's a ridiculously large number, so we're not going to right now. So this one, we got to figure out how many sets of numbers do we have here. What does this dot, dot, dot in the middle mean? Means we're missing a couple, right? Well, we can't be missing too many. We got 3 and then 6. So that just means we're missing the n plus 4 and the n plus 5. So if we count it, we have 1, 2, 3, 4, 5, 6, 7 n's that we're multiplying. So that means our first term would be n to the 7th, because you just keep adding those exponents, n to the 7th. Our last term would be what? It would be just those two numbers multiplied. Does anybody know why it would just be the 6 and the 7 times each other? Reason being, this would be 42. When you go and you distribute this, this 1 eventually gets times the n. It never actually gets times the 6 or the 7. So if you just keep going through and you distribute this one with this one, and then this one with this one, this one and this one, the ones that will be left are those last two. So it would just be 6 times the 7. They're never multiplied times an n. So that's why those two would be your last term. And it always works out like that if you have binomials that you're multiplying. Okay, last thing here. X minus 2 to the 3rd over x minus 2. They want to know if that's equivalent to x squared minus 4. So even though it's a binomial, don't we have the same thing in the parentheses? So we follow our exponent rules. If I subtract my exponents, this would give me x minus 2 squared. Which is x minus 2 squared the same thing as x squared minus 4? No. X squared minus 4, if you factor it, is x plus 2 and x minus 2. So it's not the same thing. This would just be both x minus 2's. To get that, you would need to have an x plus 2. So we got to make sure we answer the question. Are these equivalent? No. So this one, they would want to know the degree. Again, here's an example of when you wouldn't really have to multiply that whole top thing out. What would be our highest degree for our x in the numerator? X to the 10th. Your first term would be to that exponent, so your x would be to the 10th. And then our x in the bottom is to the what? Second, so use your division rules. 10 minus 2 means we would have an x to the 8th, so that means it's an 8th degree polynomial. And then the third one, again, they just want to know the degree, so we don't have to sit here spending our time multiplying the whole thing out. From the n minus 2 squared, what would our largest n be? N to the what? Second. Again, it would be n to that exponent. And then it would be times the n from the second set of parentheses. That's the largest n in that one. And what would the n be to in the last set? 3. So now if we add our exponents, we would get n to the 6th. So this would be a 6th degree if we multiplied the whole thing out. Now, could you multiply the whole thing out? Sure. It's going to take you a while, but you don't have to if it's just asking for the degree. That's a lot more work than you would actually really need to do.